Welcome to today's Explainer. We are diving right into a seriously fascinating intersection of two massive frontiers in modern science, quantum mechanics and artificial intelligence. We're going to unpack a breakthrough that uses AI not just to understand quantum computers, but to literally, physically steer them. It is mind-bending stuff, so let's get right into it. So think about this for a second. How do you control a system with uncountably infinite possibilities? That right there is the core fundamental challenge of quantum computing. We want to build these incredibly powerful machines, but to do that, we have to manipulate information in a space that doesn't just have two simple states, but an infinite continuum of states. How do we physically make that happen without the whole thing just falling apart? Okay, let's dive into this. Here is our roadmap for today. 1. Meet the quantum gates. 2. Visualize the Bloch sphere. 3. The physical control problem. 4. Physics-informed AI. And 5. Perfecting the quantum path. Section 1. Meet the quantum gates, single qubit control. To really appreciate this, we've got to contrast it with what we already know. In classical computing, a bit is rigid, right? It's a 0 or a 1. A classical operation is just a discrete, chunky jump between those two states. But a quantum bit, a qubit, is wonderfully different. It exists in an infinite, continuous superposition of states. It isn't just jumping from 0 to 1, it's smoothly transitioning through this beautifully boundless landscape of probabilities. So the tools we use to wrangle these qubits are called gates. And while there are uncountably infinite possible gates out there, a few essential ones give us our core toolset. We've got the identity gate, which simply preserves the state, basically doing nothing. Then we have the poly gates. Poly X acts like a classical NOT gate, causing a bit flip. Poly Y causes a combination of a bit flip and a phase flip, and poly Z just flips the phase. Finally, there's the famous Hadamard gate, which takes a definitive 0 or 1 and throws it into a perfect equal superposition. Section 2. Visualize Bloch Sphere, qubit visualization. Enter the Bloch Sphere. This is a super elegant 3D geometric tool. Instead of wading through a bunch of complex matrices, we can just picture the state of a single qubit as a single point on the surface of this sphere. The north pole is a 0, the south pole is a 1, and everything else is a superposition. The state is defined by continuous angles, theta and phi. And when we apply one of those quantum gates we just talked about, what we're essentially doing mathematically is just rotating that point around the axes of this sphere. It's like a giant, continuous puzzle. But, here is where physical reality starts to rear its ugly head. Pure states, so ideal qubits without any noise, they live perfectly right on the surface of the sphere. But in the real world, environmental noise and decoherence are constantly interacting with our qubit. When that happens, the state becomes mixed, and it mathematically drags our point off the surface and down inside the sphere itself. It loses its purity. Section 3. Physical control problem, steering the qubit. This is a massive paradigm shift that researchers are emphasizing. A quantum gate is absolutely not just a discrete mathematical jump. In the real physical world of a quantum computer, it is a controlled physical evolution over time. To actually realize a quantum gate, you have to steer a highly delicate physical system through time using perfectly calibrated control pulses. So bridging theory and reality is where things get wild. You have your geometric goal, say rotating a qubit around a specific axis in the XZ plane on the Bloch sphere. But to actually achieve that physically, it requires control pulses over time. You've got an omega channel and a delta channel acting as your steering wheel. To trace a path on the sphere, you literally have to blast the qubit with these precise control fields for a very specific duration. The gate isn't an instant operation, it's a physical journey. Section 4. Physics-informed AI. Pins in quantum control. And this brilliant shift in thinking is where AI steps in. Think about the old way of doing this, discrete pulse optimization. You chop time up into chunky, discrete bins, guess the pulse amplitudes, simulate it, and cross your fingers to see if it worked. But the new approach uses pins, physics-informed neural networks. The AI completely ditches those chunky bins. Instead, it models the fields and the trajectory as smooth, continuous mathematical functions, directly queried by physical time. This gives the AI absolute, literal superpowers for gate design. Because the neural network is physics-informed, it strictly obeys the laws of physics, like the Bloch equation during training. It learns the control fields natively. It maps the trajectory of the qubit on the Bloch sphere continuously. And amazingly, it optimizes the total duration of the gate entirely organically. Instead of a human trying to guess how long the pulse should be, the AI just learns the optimal timescale to complete the rotation while fighting off environmental decay. It treats the pulse, the path, and the time as one unified physical process. Section 5. Perfecting Quantum Path, the Geometric Z-Gate. Now let's look at a geometric Z-Gate. Here, the journey is just as important as the destination. The qubit doesn't just rotate to a final state. The path it takes on the Bloch sphere has to satisfy strict geometric conditions along the entire route. This ensures that the phase it accumulates is purely geometric, not dynamical, which makes the gate highly robust against certain errors, but it demands absolutely perfect coordination. At every single instant along these reference loops, the control fields generated by the hardware must be perfectly perpendicular to the state's path. So the crucial point is figuring out where this all breaks down. Because the PIN AI maps the whole continuous journey, researchers could actually read the AI's internal process and diagnose exactly where it struggles. And guess what? The bottleneck happens precisely at the sharpest turns on the quantum path. When the required control direction turns the fastest, which is a metric called the turning rate, or kappa, that perpendicular coordination slips and the geometric errors just spike. Once they saw this bottleneck, well, the solution was incredibly elegant. They fed this local diagnosis right back into the AI's training loop. By applying a turning-aware weight, essentially giving a higher penalty, or beta, exactly where those sharp turns happen, they added design pressure right where the path is hardest to navigate. And it magically fixes the bottleneck. Actually, it's not magic, it's math. The AI simply readjusts the fields and trajectories continuously to absorb the correction, dropping the error at the turns without ruining the rest of the path. The outcome of giving AI this physical, continuous view, honestly, it's staggering. They achieved a phase-closed geometric Z-gate that thoroughly suppresses dynamical phase, completely eliminates those nasty turning errors, and hits a process fidelity of over 99.999%. It proves without a doubt that AI can learn, diagnose, and perfectly refine a physical path to create incredibly stable quantum operations. So what should you actually take away from this explainer? It's this. Quantum control is no longer some dark art of just guessing discrete waveforms. By representing the control sequence as a continuous, physics-informed neural network, the entire evolution of the qubit becomes a readable, diagnosable, and refinable physical process. This isn't just neat theory. This is exactly the kind of deep, automated physical refinement we absolutely need to scale up stable, real-world quantum computers. Which leaves us with a truly thrilling thought. We just saw AI seamlessly learn the continuous physical evolution of an uncountably infinite quantum system. If AI can do that, if it can decode and perfect the invisible path of a single qubit, what other complex, invisible physical processes in our universe will we use it to decode next? Thanks for joining me on this deep dive. Stay curious, and I'll see you in the next explainer.